Hello and welcome to Physics for Students. My name is Shaunak and I welcome you to yet another video on differential geometry. First of all, let me wish you a very happy new year and let this 2022 be much better than the earlier one and let you prosper and be healthy and have more knowledge on various subjects. Well, today's discussion is how to learn differential geometry. So the basic point of this video, my intention is to make you aware about how to proceed on the way to learn differential geometry. As you know, differential geometry is a subject which encompasses various ideas, thoughts, most importantly, a lot of mathematical knowledge and disciplines. So often the students get confused at how to learn differential geometry, where from to start, what are the initial things that they need to have. So this video is intended for those who are looking for a guidance to start learning differential geometry and proceed one by one. However, there will be a lot of subjects that you might know or you might not know, but this video is not meant to go deep into this subject, but just to give you a guideline, a roadmap to learn differential geometry. So let's get started. The very first thing that we need to understand when we are learning with a topic called differential geometry is this. Now, as you can see in this picture, I have given two divisions. First of all is that you do have the required background and you started studying. And second is that you have a basic background and then you can learn as you study. Now, for those who already have a very strong mathematical background and you already know that, okay, these are the things that I need to have and I can just continue to study. In that case, that is not a problem. But as you understand that most of us, especially the students, we generally, you don't have that kind of a time that you completely learn for certain years the areas of mathematics and go and do exercises and get a solid foundation. So you opt for the second option. That is, you study. You continue to have a basic background and then you continue to learn differential geometry and keep on studying on those which are really unknown. Now, the problem that arises that when you're going and studying unknown, then what happens is that you study certain chapters, okay, when you don't know, and then further go back, then you learn the unknown, then again come back, again go back. In this way, it goes on. So what happens is that you generally tend to lose the path or the right direction where you're going. So you are going through certain path and then you come up with, for example, with a topic called Christoffel symbol. Okay, you go understanding Christoffel symbol. Now, when you're studying Christoffel symbol, there are further things called Levi-Civita connection, parallel transport, covariant derivative, and then you go further and then you get lost. So I would just like to give you an example how you should go ahead. So in this picture, what I have done is that I have given a very basic, definition of Riemannian manifold. So as you can see on the screen, the definition is there. So the mathematical field of differential geometry, in the mathematical field of differential geometry, Riemann curvature tensor or Riemann-Christoffel tensor, which is named after Bernhard Riemann and Elvin Bruno Christoffel, is the most common way used to express the curvature of Riemannian manifolds. It assigns a tensor to each point of a Riemannian manifold. It is a local invariant of Riemannian matrix which measures the failure of the second covariant derivatives to commute. A Riemannian manifold has zero curvature if and only if it is flat, that is locally isometric to the Euclidean space. Now you see, for example, this is an unknown definition and you really don't know what is Riemannian curvature. So those which I have highlighted here in red, these are the unknown factors. For example, express the curvature, Riemannian manifolds, local invariant, and failure of the second covariant derivatives to commute, and locally isometric. Okay, so what you now need to do is just understand those areas which are not known to you, and don't go much deep into that. So first you understand, okay, it expresses a curvature. Point number one, clear? Second, you see it is a Riemannian manifold. So you just go to the internet or to the dictionary or to the book and understand what is a Riemannian manifold. It is an n-dimensional manifold which generalizes Euclidean space or the general manifold structure. Next, what we come to know is that it is locally invariant. That means locally, that is in local Euclidean space, it doesn't changes. That is another point. Next is that failure of the second covariant derivatives to commute. So you might be stuck at this point. Just try to understand that if the space is flat, then the covariant derivative becomes ordinary partial derivative, and if the plane is not flat, then they do not commute. The the partial differentials do not commute, and Riemannian curvature tensor is the measure of the amount of that how much it doesn't commute. That means if these two factors are commuting at each other, and if they are not commuting, that means Riemannian curvature tensor is giving you by how much degree they do not commute. And it is locally isometric, that means it is similar. So in this kind of a thing, what you get is that it expresses curvature, one. It is of Riemannian manifold, which is n dimension. It is locally invariant, that means it locally won't change. And it is a failure for the second covariant derivative. That means in general flat space, the partial differentials commute. Here, obviously, it is not a flat space, so they do not commute, and they measure how much they do not commute, and they are locally isometric. Now, what is happening is that I am not going further into what is a covariant derivative and what is a Christoffel symbol, who was Alvin Bloom or Christoffel, otherwise I will get lost. So I have got the basic idea of those key points, and I have understood what is a Riemann curvature tensor. This is the type of approach which I would suggest for those people which I have measured in the second point, that you really don't know and you're slowly going ahead and learning. So just to make you understand, look at this picture. I have given what you need to do. First, you need to get the basic idea. Second, do not go deeper into the details. Third, create an idea of the concept, visualize and read it once more. That means you need to read it if you don't understand once more, then the second time and the third time, right? So that you don't go much deep, so that you get lost. You create a basic idea. Just close your eyes and try to visualize what it is and read it once more. So this is basically an approach, a kind of a guideline for differential geometry, or you can generalize into other areas of physics and mathematics and chemistry also, which you might follow. Another important point which generally people make a mistake is that, for example, nowadays the young generation are all learning online. Right, so there are two modes. Here in the picture, if you see, I have given, there are two ways of learning. One is that you are learning purely online through books, through PDFs or online YouTube lectures and researches and blogs. And the second one is that you're going through hard copy books, library, consulting research papers, etc. Now, the problem with online learning, which I have found most of the students that they do, is that when you go ahead with online learning, say for example, this example, Riemannian curvature tensor. So you click on what is a Riemannian manifold, right? You click on that, it shows you something. Then there is another hyperlink, it shows you something. Then you go learning another, it shows you something. So 3-4 clicks and you went deep into the details. When you come back to what is a curvature, you forget. This is the problem with online learning. Whereas in books, you really have to go ahead and purchase another book, or you may have to search. Because in our days, when we used to consult book, we didn't have that amount of option, right? That I go to this and this and this and go ahead. So we have to consult with the professors, lecturers, or maybe go to the library to get ahead with books. So my suggestion would be, if you are learning online, great. But as I told you, don't click and go into further details. You will be lost. I'm telling you, you will be lost. When you come back after 3, 4, 5 clicks, you have really forgot that what you were learning. So my honest suggestion would be that those who are learning with the first one, that is the online and not through books, it is great. Everything nowadays are online. With COVID stuck in, we get more online resources, but do not click much, do not go further. Just try to understand moreover whatever it is, and then try to go on reading this idea. I'm telling you, with my years of experience, you cannot learn something just at one go. You have to come, and I am telling you, with maturity, things mature and you get a better understanding. So just go on learning the basic ideas, and with the passage of time, once your maturity grows, when you come back, you will see you have got a better understanding. So if you click and go, you get mixed up, you get confused, and you get into problems. So just follow the basic idea, understand the basic things, and then create an overall picture. Over the years, slowly this concept will get into your mind, into your head, and you will get a better understanding. So this is the second guideline when we are learning differential geometry. Let us keep it in mind. Okay, now this is a quite a common question. I also ask this question in my physics students forum in LinkedIn. Now, when I talk of the prerequisites of a differential geometry, it actually depends what level you are learning. Are you into undergrads, or you are a postgrad, or you are going into research? So what level you are learning and what book you are reading, prerequisites of differential geometry depends on that. Now, what I would also like to tell you is that, as you have seen in my first video, I am very thankful the amount of likes and people who have viewed. I have told that topology and differential geometry are somehow related to each other, but in the first video I told that let us keep apart topology. Right. So here also what I would like to tell you, that let us keep apart one part of the study, and because otherwise it would get too complicated and it will take a lot of time. Right. So prerequisites of a differential geometry, if you ask me this question, first of all, I would ask you which level you are studying. If you're going deep into research and deep into pure differential geometry has two parts, the modern and the classical one, then you would require a lot of things to do. Also even topology. But say for example, you are undergoing differential geometry to understand general theory of relativity, or to get an overall but a very good solid foundation, then what I would say is that you see in this picture now. So I have made two notions. One is the basic. Actually, to be very honest, if you technically say, then topology won't be required. What you require is this: multivariable calculus, linear algebra, Euclidean 2-dimensional and 3-dimensional space. And you see in the rigorous part, I have written that you need all those first, and also you need tensor calculus, mathematical analysis, which I mean to say complex, real analysis, functional, measure theory, and so on. So now the question is that really what you need. So technically you don't need, you just need multilinear algebra, you need very good foundation of partial differential equation, and you need to have a complete, I would say, conceptual understanding of what is an Euclidean space, both in 2-dimension and 3-dimension. And if you want to go deeper, then you need all this, and you need a very good understanding of tensor analysis and real analysis. And if you further go into research, then maybe also, yes, quite a good portion of topology. So this is what you need as the prerequisites depending on the approach. Technically, you need all those three, but if you go further deep, you need all those things which I have shown you in the picture. Now we come to the very important question: really, do we need analysis to learn differential geometry? Now see, the question is that when you are learning differential geometry in a very rigorous manner, or in a very basic manner, in both these ways, I would say yes. you need to understand real analysis, because otherwise what will happen that you will you will miss out a lot of on topology if you don't know analysis. So it is difficult to tell. I would prefer you that you should know analysis in order to learn differential geometry. The reason is that you see, differential geometry is a study of local manifolds or surfaces. Topology is also a study of surfaces, but from a global point of view. So when we are talking about the study of surfaces, definitely real analysis is something which is required. Now you will miss out a lot of understanding if you don't know really what is real analysis, because there will be a lot of overlapping factors between differential geometry and real analysis. Here is for you a basic definition. For example, in this picture, as you can see, the definition of a continuous function between two topological spaces is this. Right. So you can understand that without analysis, it is very difficult to make you learn. Now, if you see in my earlier video where I have given that topology and differential geometry are already related. So just you can read this definition right over here. So continuous function has been defined as that. So how will you come to know particularly about this kind of a definition if you don't know real analysis? So yes, real analysis is very important. You need to understand real analysis before going and studying into differential geometry. Look into this definition. Now, if you see that this is a definition, typical, very simple definition of what is a manifold. Now, you see, I have written manifold is a topological space that locally resembles Euclidean space. So what is a topological space? If you go back to my video on what are the basics of topology, you will understand automatically. Again, you need to know what is real, you need to know analysis. Otherwise, this very basic definition of what is a topological space in order to define manifold doesn't work out. Understand one thing, that this differential geometry is a study of real analysis on a local level, and what the basic aim of differential geometry is to live the knowledge of real analysis from there to the manifold level. So the basic idea is that whatever real analysis you know, it gets elevated and it gets used into the manifold level. Now, you might have a question. Look into this picture also. This is a wonderful book. Okay, it is called Topology from the Differential Viewpoint. And I have given also the table of contents. If you really don't have that book, you can just let me know in the comment box of the video. I can email you. It is a wonderful book of Professor Milnor. It is 76 pages of book, not much into that. And it gives topology from the differential viewpoint. Now, I don't want to go into what is a differential topology, because there are different divisions of topology. What I'm trying to tell you is that the topology that you really need to know, as I will just show you in the next part, that you can learn differential geometry without topology, but topology from a differential viewpoint. That means I'm not learning topology as a general topology. I want to understand topology on a differential viewpoint. Why? Because I am learning differential geometry. So you can just quickly get over this 76 pages of book, differential topology from a differential viewpoint. So you can just understand topology from differential viewpoint and you can understand this. So yes, to summarize this part, that you need to have a solid knowledge of real analysis. So go ahead with differential geometry, because you will miss out other things. But yes, I can tell you, if you just get to know about these terms which I'm showing on the screen, then you can just ignore topology, because these terms will give you more or less a basic idea of what part of topology you need, although ignoring topology and starting with differential geometry. Good point is to get ahead of this small book of Milnor, which shows topology from a differential viewpoint. These two books of differential geometry, one written by Andrew Priestley and other by Thomas Bancroft and Stephen Lovett, assumes that you really don't need to know the knowledge of general topology before you embark into the journey of differential geometry. In the first book, the author, Andrew Priestley, writes, which I have underlined it in red. For readers unfamiliar with point set topology, this means roughly that C is in one piece. For example, the circle x squared plus y squared equals to 1 connected, and so on. Further going, the author writes, we shall not prove these assertions as a proper discussion of simple connectedness would take us too far into the realm of topology. Further going ahead, the author writes, the reader should feel free to either skip the technical details of the proofs in the rest of this section or refer to 22 Appendix A for background material. Further, the author writes, similarly in the field of algebraic topology, a topic that is outside the scope of this book, one can define the degree of a map between spheres and so on. Now, as you can see that these two books which I have mentioned, again, if you don't have this book, do let me know so that I can send it to you. These two books do not consider topology, yet teaches differential geometry in a wonderful way. Andrew Pressler's book is just a Bible, and it goes step by step. It is a beauty. So my basic objective of making the earlier slide was to make you know and really show you that you really don't need to know topology. But the viewers might disagree with me. Yes, those who are going much more into research and deep study of differential geometry, you have to know topology, real analysis, linear algebra, and all those things which I told, and start learning differential geometry. Anyway, the basic is that you can understand differential geometry without knowing topology, as I have shown you. Now, in this part, we almost covered the first part of our video. So we really know, okay, these are the things and these are the approaches. Sorry. Now, what you need to now, we will start with the, as I told, we always rely upon the Greeks. So we will start with Pythagoras' theorem, and we will move ahead with the metric, because a Pythagoras' theorem and this one which I will show you, you might know a lot of topics, but it is a good time to connect the dots and get a bigger picture. Anyone looking at this figure can identify what it is. It is the plain and simple Pythagoras' theorem, which is developed in a description of mapping in the plane geometry that was extensively used for the later century by Euclid of Alexandria. Now, this is the simple flat geometry, and what it says is this. It is quite simple. I think that I don't need to repeat it again. So this is a simple flat geometry, and nearly it records the spatial geometry in which we live is called a Euclidean geometry, which is more or less known. Now, Pythagoras' theorem describes actually the distance between 2 points in an Euclidean 2 or 3-dimensional space. Let us consider this figure. There are two vectors, r1 and r2, and let us say r3 equals to r2 minus r1. So the Pythagoras' theorem allows us to determine the length of the vector r3. So it is this. Now, if the components of this, I would say typical prototype vector r is this, right? So if the component of this vector r is this, then the Pythagorean theorem, we can tells us this, which leads to further this. So the components are further expanded into this. Now, it might not look kind of a simplification of this description, but we can rewrite, or we can further write the latter form as this, right? So this can be written further as this. So I think this is quite clear. So given the length of the vector r3 containing its component types, we can rewrite this, and then we can write the latter part into this. Now, if we can write this in a linear algebra form, it looks something like this. Okay, taking the dot product and further. Now what we get is that this 3 by 3 identity matrix, okay, it is a form of a type of a metric, we can tell, because we are trying to show the generalization of Pythagoras, how it gets into metric. So it is a kind of a metric which we can call the total is the measurement rule. So for calculating square lengths via Pythagoras' theorem in a 3 Euclidean space. Now it actually tells us that the spatial geometry or the space is involved in length measurement. Now here the rule I understand is extremely simple because of a choice of coordinates. It is Cartesian and the space is Euclidean. Now while it might not clear, then this form can be written in this form, okay, which we can call as a tensor form or a tensorial form, right? So it can be further written into tensorial form, where this delta x sub I and delta x sub j are actually representing delta x, delta y and delta z as usual. Now you need to note that the summation is implied here as per the, so if we use the Einstein summation convention, we get this. So we use the Einstein summation convention and we sum up and we get this kind of a figure. Now moving further, what we get, this one is actually the metric tensor of a Euclidean three-dimensional space in Cartesian coordinates, in the Cartesian measurements. Now under this spatial conditions, for example, this rule holds globally. That is, we can measure the square distance, that means how big or how large it can be between any two vectors in a flat space. Now it might not be obvious, let us remind that whatever the orientation of the origin, whatever the way it is, it moves, we use for our coordinate system delta L, which remains invariant. That means it doesn't change. And also it implies that whatever be our perspective where from we are looking, the length of the vector R3 is seen to be the same. So these are the 3 important measurements: metric tensor of a Euclidean three-dimensional space, delta L remaining invariant, and R3 is more or less wherever we look it is the same. Taking things forward, we can extend the Pythagorean theorem, say for example in more generic conditions, so where the space might only be flat locally, I mean to say the space is flat locally, then we can write this, right? If the space is still globally flat, then what we can do, we can further integrate this dl factor along a straight line from R1 to R2, right? And what we obtain for the delta L is this one. This is a nice integration what we have done. Now if the space is this is what we get. Okay, now if the space is not globally flat while still being locally flat, I mean to say we are dealing with the local part, the shortest path from R1 to R2 may not be the simple line. Okay, so from R1 to R2, whatever you can go back into the figure, it might not be a simple straight line, and what we get is something with this shortest path from R1 to R2, and this is known as a null geodesic. So now you see from Pythagoras' theorem how we applied, extended, then got a metric tensor form, and then we integrate, then we consider something to be where the space is not globally flat but at least locally flat, and then we get the shortest distance, which is not the straight path, which is something which is called a null geodesic. Now this path, which is called the null geodesic path, everywhere locally along the path, if we assume that a photon travels with a speed of light in a straight line, suppose the photon always feel itself to be traveling in a straight line, but a straight line actually is very much curved to us from relatively static perspective, as a photon is accelerated towards large masses. Anyway, remarkably, what it will happen that the photon may take many paths of exactly equal lengths from the source of the detector, and the effect is what we call is gravitational lensing, when the light is bent by strong gravitational fields. Anyway, I am not going into further into that. This can be further extracted into special theory of relativity, but in general in general this is what happens. So if the space is not globally flat while it is locally flat, the distance between two vector points r1 and r2, this is mended by this, and this is actually what is called a null geodesic. Just to show you that how we started, if you go back to the previous few frames, you will see that we started with Pythagoras. Then what we deduced is that we went into a linear algebra form, and then we took this 3 by 3 matrix. Of course it is quite easy because we took the Cartesian path and we made it clear in a tensorial form, which can be further expanded into Einstein's summation convention, considering that this metric tensor is holds for Euclidean space, as well as delta L remains invariant, and R3 will be the vector is seen to be the same. We extended the Pythagorean theorem in which space might only be locally flat. We got the DL square factor, and then further integrating we got into what is called null geodesic path. Now, as you can see from this video onwards, that we are now moving into the field of generalization. Now, when we move into the field of generalization from the Pythagoras, we are applying the Pythagoras theorem, because I really want to show that how this generalization have proceeded and how we are moving ahead in the road of differential geometry. So now in this picture, what you can see that you can take a snapshot, because there are few points which I have mentioned. So the Pythagorean theorem gets generalized to inner product spaces. That is point number 1. Second is that the concept of perpendicularity is replaced by orthogonality. And another point is that there is a difference between perpendicular and norm. So the concept of length is being replaced by norm. Now there might be a question, what is the difference between perpendicularity and orthogonality? Yes, there is a very subtle difference, but this is not the right time to do. So understand that there is a difference. The inner product spaces you can see is there on the screen, and it leads to further generalization, right? So this is a kind of a picture which gives you that how from Pythagoras' theorem, how we are generalizing to inner product spaces, perpendicular and orthonormality, and further generalizations. So this is one thing which gives you an idea that we are now expanding our study from Pythagoras' theorem and metric into further generalization. This picture, I am sure you have seen it many times, but this is a good point to let you know, because this is actually the rotation of the coordinates, and as you can see, the length remains the same. You can see it in the picture that the green vector remains the same. Now, why I am telling you all those? Because these are the ways in which you need to proceed. These are the learnings, these are the concepts that you need to have. So now you see that rotation of coordinates from one frame of reference to other, the translation of a matrix and how you write, all these are intent. And why? Because this is another step ahead for learning differential geometry, the local invariant concept, and this will actually lead to tensors. Next, right on your screen, what you can see is that once we apply Euclidean coordinates to other coordinate system, so you can see Euclidean coordinate is applied to polar, spherical, and other coordinate systems, right? The polar coordinates and the Cartesian coordinates in terms of spherical coordinates, the distance between 2 points was also changed, and how that change of the Pythagorean formula for distance in Cartesian system as expressed in polar coordinates. So again, as you the basic intention of making this slide is that you can see that the old concept of metric, once we proceed in differential geometry, how it is getting changed. So for you, it is extremely important to know how the coefficients of Pythagoras, or the general, for example, the length calculation, the coefficients are generally changing, and what are the additional coefficients, the sine theta, the cos theta, the r factor, how these things are coming as we apply the traditional concept of length measuring to other concepts. So this is the reason I made it, so that you also learn and have a solid foundation of transforming the usual metric into the other coordinate system. So coordinate transformation is a must. You should go ahead with that. You should also note that how the Pythagoras theorem, when it is applied to non-right angle triangle, here is there on your screen, that it is called the law of cosines. Now you might disagree with me. I know that you know all those things, but I'm just giving you a path, a kind of a guideline, a roadmap, that this is also important. You need to know the law of cosines so that you can understand when it is applied to non-right angle triangle how this works. This one, exterior forms and exterior calculus. I would like to tell you, my dear, this is very, very, very important. As you can see on the screen, why we need exterior calculus, because functions which is used in general to calculus is now being generalized to what is called a differential form. Now hold on. Differential form is itself another subject. I don't want to go into this. We use a kind of this lambda sign to denote exterior, what we call exterior product. And what is the concept? I think, yeah, it is called wedge product. I think it is so. It is called wedge product. So exterior calculus, I will like to show you again on the screen. It is important because it extends the concept of differentiation from functions to differential forms, and most importantly, you can see it generalizes the fundamental theorem of calculus and makes it metric independent. As I have been telling in this series of videos on differential geometry and relativity, that our basic aim is to generalize and make it coordinate free. We won't depend on any coordinate. We won't depend on any frame of reference. It will be totally coordinate free. So exterior calculus, exterior form, exterior derivative, it is important because the concept of the function which is there in calculus now gets much elaborated, now gets into what is called differential form, and we are making it metric independent. So yes, we need to know what is exterior calculus. I've given you a more or less idea of what is exterior calculus. Go ahead and learn exterior calculus. Tensor products or tensors. Here it is on your screen. You can also refer to my video in this Physics for Students YouTube channel, where I have given more or less a good comprehensive idea of what is a tensor. Now that we know, for example, the generalization, the application of what you call Euclidean system to other coordinate system, coordinate transformation, spherical and other coordinate system, now comes the concept of tensor. So the concept of tensor is the central before you go ahead and start differential geometry, because tensor encapsulates, well, I won't take time again to explain what is a tensor. It is not there in my general theory of relativity. You can just look at. So tensors, you need to study basic idea of tensor, tensor calculus, gymnastics of the index, Einstein summation convention, covariant, contravariant tensor, mixed tensor. You can refer to my videos in tensor and go to my video on what is metric tensor in general relativity. It will give you an idea. We need to know because it will encapsulate everything, and we will proceed now with the concept of tensor into the other, as you can see, quadric surfaces are important. Now, okay, let me tell you. Now, you saw the way we are proceeding. We learned with the prerequisites, the approach, the Euclidean space, generalization of Euclidean space, tensors and approaches, exterior forms. Now you will see that as I talked earlier, the differential geometry is basically applying calculus to geometry, right? So here on your screen, you can see that we are now, you need to learn quadric surfaces. So you can see there is an ellipsoid, a cone, a hyperboloid of one sheet, and a hyperboloid paraboloid, along with the formula which is given. Now, why I am telling you this is quadric surfaces, because you now need to apply calculus 3, and you are now already have started applying, I mean to say, algebra into calculus. I will just show you how we go from algebra to calculus. So quadric surface is important. Another important part is that you also need to learn how to calculate the length of areas, right? The calculate here it is on your screen. So from cylindrical to rectangular, cylindrical to spherical, spherical to rectangular, rectangular to spherical. So all these things you do it on your own hands, how these transformations and calculations work. Why? Because these transformations will give you an idea that how the things are changing from one coordinate system to another. So now we are on a phase where we have already applying algebra to geometry. Quadric surfaces very important, and the change of coordinates from the Cartesian to spherical, polar or whatever. Do the sums at your own. There are good amount of resources in the internet. You can also write to me. I will tell you how to go ahead. This is very important. Next thing would be Green's theorem and Stokes' theorem, right? And I have made a note that you also need to learn integrating differential forms, curves, surface and areas. Because as I told you, in general, in differential geometry, we differentiate the manifolds and we integrate the curves, area and surface. Both of them works each other, but most important is Green's theorem and Stokes' theorem, because these are again generalizations. Now, you see, we already know what is a vector algebra. We know what are the operations that we do in vector addition and all those tip to tail method. Here on your screen, you see that I have given a kind of a approach. From vector algebra, it gets generalized into geometric algebra. And from geometric algebra, it gets further generalized into geometric calculus, because geometric algebra is an extension of vector algebra. So what is happening out is that, as you already know the operations of vector algebra, you apply vector algebra to geometric algebra, which I told you is the quadric surface. Now you can see that how we are sequentially proceeding. If you don't know quadric surfaces, geometric algebra, you won't be able to move into geometric calculus. So understand what is vector algebra. You already know vector algebra. Then go into geometric algebra, and then further you can go into geometric calculus. Geometric calculus is basically, it extends the geometric algebra to include differentiation and integration, and embraces differential geometry and differential forms. This is what I was telling. The differential form itself is a study. I don't recommend you to go much deeper into differential forms, but you should understand these things, that geometric calculus, why geometric calculus you need to understand, because it will extend geometric algebra and include the operation of integration and differentiation into differential form. And differential form, as you have seen earlier, is something which is metric independent and coordinate free. So this is a kind of a guideline. Now look into this picture. This is a kind of a overall idea of what is geometric algebra. So it gives a summary of what is geometric algebra. It is an extension, obviously, of vector algebra. It is coordinate free, and operations are represented by geometric algebra. You can take a pause and take a quick note of the screen, because this is overall what is the concept of geometric algebra, and you should really know that before studying why you should study geometric algebra, because it is going from one part to another. That means we are moving into generalization. The next picture, look into your screen. This gives you a basic idea of what is a geometric calculus. It summarizes important points. It elaborates, obviously, geometric concept. It provides invariant formulations. And as you can see right at the below in the screen, I have given the fundamental theorem of geometric calculus. The fundamental theorem of the general calculus, as you know, integration, differentiation, how they are reversed and get cancelled over each other. The same fundamental concept of classical calculus gets generalized into the fundamental concept of geometric calculus. Right. So let me, before I move into the next part, I hope you understand that the calculus 3, the quadric surfaces, spherical, rectangular, the movements, I mean to say the coordinate transformation. Then you learn the integration of differential forms. Then then you go into geometric calculus, and geometric calculus further gets expanded into geometric algebra, and then it gets further into geometric calculus and the essential points of geometric algebra and geometric calculus. More or less, we have almost come to the end of the road in which we are moving, the road towards differential geometry, and then we will move on what we call is geometry of surfaces. Well, as you know, geometry of surfaces starts with the legendary mathematician Carl Friedrich Gauss. Here, have a look on your screen. I know that the topics are quite huge. So theorema egregium, which you already know, deals with the intrinsic part. So intrinsic and extrinsic geometry, get a good concept of that. First and second fundamental form, very important. What is an ambient space? Geodesic curvature, and so on. So geometry of surfaces is important. One thing you might be confused, there is a very common term which is used, which is called an ambient space. What is an ambient space? Now, for example, a particular object, okay, how the space is around that object. How the space is around that object, that is called an ambient space. So just wanted to tell you on a good note that don't get confused with what is an ambient space. Now, geometry of surfaces essentially deals what you learn, I mean to say quadric and differential forms, integration, geometric calculus, and geometric algebra, etc. Now we are studying what is called the geometry of surfaces. That means, as if you can go back to my previous video, I have explained the motivation and influence of geometry of surfaces, which was first developed by Carl Friedrich Gauss, that here is a surface which is bent in a very crazy way, and there's an ant living over there. Without looking outside, how I can understand the geometry, intrinsical geometry. So that is why I told first and second fundamental form, very, very, very important. You should have a complete good understanding of what is the first and most importantly, the second fundamental form. You also need to come to know about the geodesics, the curvature, how the curvature curves. So have a good understanding. Geometry of surfaces, why I am calling, because this now we are coming to the end of the road to differential geometry. So the surface, the geometry which is leading to the surface, that is intrinsically, not extrinsically. So you need to understand those concepts on a very good. The last and the most important, as I have mentioned, the granddaddy of mathematics and geometry, Bernhard Riemann, and what is called Riemannian geometry. Have a look at your screen. I know it is quite an extensive, so you need to understand what is the calculus on manifolds, the Riemann curvature tensor. If you see in the bracket I have written non-commutativity of covariant derivatives in different direction. I was just speaking about this in the earlier part of the video. Ricci curvature, okay, the Levi-Civita connection, covariant derivative, Christoffel symbol, and metric tensor. And you can mention that in my video on general relativity. Now, the question is that it is quite an extensive, I really understand. Now, Riemann curvature tensor, Ricci scalar, Levi-Civita connection, and covariant derivative, Christoffel symbols, these are actually, related to each other. As I told in my previous video, the differential geometry has got two parts. The first one is that, are you willing to learn differential geometry as a pure mathematician, or you want to go into pure mathematics? Right? Or you want to understand on a basic level, I mean to say in a general level, and understand Einstein's relativity. So these points of Riemannian geometry, which you can see right now on your screen, this is something which is coming very close to relativity, especially general relativity. So this requires not much of a difficulty, I can tell you. Levi-Civita, Christoffel, if you can go back to my video on Ricci scalar, which is there in the playlist of general theory of relativity, you will understand. It is simple. If you got an idea, I can tell you, don't get confused. If you've got an idea of tensor calculus or what is a tensor, you can understand those things because these are all related. Levi-Civita, covariant derivative, Christoffel symbols, I have shown that. No problem. So this actually concludes our journey on what are the essentials and how we go ahead in learning differential geometry. So that's it. I mean to say we have more or less completed what I need to tell you on the roads of differential geometry. Now you might have a question that, oh my goodness, it's quite a huge one concern. I have consulted a lot of professors. I mean to say, I have consulted with a lot of my students who are doing pure study in differential geometry, and they have told me, yes, it would require some time. I cannot tell you, the number of, I would say, time, the hours that it would require. But as you can see, that it encompasses and embraces a lot of fields in mathematics. Right. You start basically with linear algebra, then you move into partial differential equation, then you move into tensor calculus, then you move into quadric surfaces, then you move into geometry calculus, you go move into differential manifold, then you move into Riemannian geometry, then you move into geometry of curved surfaces, invariance, Gauss's theorem, a lot. But actually that is what is differential geometry. You need to have a very good understanding of a lot of concepts. And my basic intention of making this video is to give you an understanding that how you should go ahead. Yes, I know I have not mentioned the names of the books because the video is quite long. So in the next video, what I will do is that I will show you just few, not a huge amount, just few important books, and which book you should start with. Importantly, which book you should start with reading with differential geometry. So just to summarize today's video, so what we have done is that we have first learned the approach. Second, how you should go ahead in learning differential geometry on an online and an offline mode of learning. Then we talked about the prerequisites. So again, prerequisites cannot be told like that, because prerequisites means what? That which level you are studying and which book you are studying. But I have shown you the basic prerequisites and a very rigorous prerequisite, because if you're going into deep study and research, you should come back with topology. Otherwise, technically, linear algebra, multivariable calculus, which I have shown. Real analysis, yes, you need to know real analysis before going into differential geometry. We also learned that can we learn differential geometry without topology? I've shown you two best books which you can email me, I can send it to you. Without a notion of topology, you can start with differential geometry. We learned about Pythagoras' theorem, how it gets generalized to metric, what are the important perpendicularity, length is replaced by normal, rotation of coordinates, Euclidean coordinates applied to other coordinates, exterior calculus, exterior forms, differential manifold. Also, we learned about quadric surfaces, different type of quadric surfaces, calculating the length of areas, integrating differential forms, curves, etc. We also came to know what is called geometric algebra, which is also called a Clifford algebra, how the generalization from general vector operations go into geometric algebra and then into geometric calculus. We also learned about, you should know about geometry of surfaces, first and second fundamental form, Gauss's theorem, and embedding surfaces, all those things. And lastly, which is much more bent towards general relativity, is Riemannian geometry, Levi-Civita connection, tensors, covariant derivative, Christoffel symbols, metric tensor, and Ricci curvature tensor, Ricci curvature. So that's all. So I just thought to give you a summary. Don't worry, I know that it is quite an extensive, because it will require a lot of energy, time and dedication. But I can tell you that if you follow the guideline which I have tried to show you in this video, it won't be difficult. After all, we need to start somewhere, right? So if you keep on thinking and thinking that where do we start, it becomes, it is not a good point to do. So with this new year coming up, you start starting with differential geometry, and I will make another video on the books and what are the books that you need to read and what are the books that are very intense and what are books which are very basic, and I will show you a complete guideline. Goodbye till then. Please do like and subscribe and put up your comments on the comment section of video, and stay happy and make this new year much more fruitful, and stay healthy. Bye.